Hi, I'm Marcus, and today I'm presenting the tutorial on load forecasting here at the Climate Change AI Summer School. I'm with Birds on Mars, we're a small AI consultancy where I'm responsible for AI and sustainability topics. Before that, I had a background in research where I was working with smart meter data on load forecasting and other optimization in the context of building and local energy management in districts. At Climate Change AI, I'm a core team member where I'm currently the community lead for buildings and transport. But let's jump right into this tutorial. So as the other Climate Change AI tutorials, the best point to get started is basically if you go to our homepage, tutorials, and there you find all the other tutorials and also this building load forecasting one. Of course, you can also go to the GitHub. And if you go to GitHub, you can, for example, open this in Colab, or you can download it and run it in your local, let's say, IDE. But today, let's work in Colab. And yeah, this is a second iteration of this load forecasting tutorial. It was firstly created for the summer school 2 years ago, but has been improved since then. What's the key learning objectives? So we are going to use off-the-shelf machine learning models for some time series forecasting. Some of the concepts may be applicable also to other time series tasks, but of course the motivation here is building load forecasting, but it may be actually some of the concepts again for load forecasting more generally. And then there's some common pitfalls also again when working with time series and load forecasting. I'm not going to give you the perfect model today, so don't have this expectation. It's more about giving you some of the tools and introduction to the tools that you can use as a starting point to get working in this area. So what will we do today? First, I introduce a little bit to why we're doing it in the first place. Then we're going to talk about using machine learning for load forecasting task. We're going through a case study where we do each of the relevant steps. And then I'm going to tell you some of the common pitfalls and give you some more references for reading. Actually, I'm going to start by mentioning two that I believe are relevant references already. So because I'm going to reference them all over the place. One is a book that I've been co-authoring. It's an open access book, so you can freely access it at Springer. You can go into each of the chapters here on the page. You can download the whole book as a PDF. And this covers a lot of the content that we're doing in this tutorial today, and of course goes into much more depth. So also this introduction that we're doing, talking about machine learning in this context and how to actually do proper load forecasting in the area. Here we framed it as low voltage load forecasting, but this applies also to a lot of concepts in the area of building load forecasting. The second one is a review paper that I've been co-authoring. It's not an open access paper in the journal, but we have a preprint of the journal version that you can also look at, and it will also discuss some of the motivation and give you an overview of a lot of research that is happening in this area. It's by now 2 or 3 years old, so not perfectly up to date, but may still function as a starting point. Good, let's start with the introduction. So why are we needing load forecasting in the first place? So they're just a useful input to informing a lot of usually optimization tasks, right? So you need optimal forecasts for the next minutes, hours, days, as we will see, to make more informed decisions within many applications. So this can be, for example, in the power system more generally. So for example, there's also a tutorial, for example, there is a tutorial on, there's a tutorial like if you go, for example, to the power, there's a lot of tutorials that actually use, here, there's, for example, the optimal power flow tutorial, where buildings are one part of the power system, of course, and if you want to do the optimal power flow and want to incorporate especially like a lot of renewables, so you have an optimal power flow with uncertainty. In order to do that properly, you need forecasts for the next minutes, hours, days. And Eventually, like for energy management applications, for example, in districts, you also need forecasts. For example, here we have the City Learn tutorial, which is also part of the summer school, but there's also the Bob test tutorial, which is also part of the summer school. Both of them are doing optimization locally within your buildings, within your districts. And as you see, building loads are one part of the input to these sort of optimization problems. So in order to do this properly and most optimal, it makes sense to have forecasts of what's going to happen within the next minutes, hours, and even days. And for that, you need forecasts. But of course, there's also a lot of other applications. And you can actually have a look at this review paper where we talk about more, which may or may not be applicable also to climate. For example, there's of course also grid theft. But a lot of this is related to climate. For example, if you reduce peaks, you can incorporate more of the new electrified loads like electric vehicles. But yeah, I recommend reading more in this book and the review paper. And then forecasts are relevant at different time scales and different spatial scales. Let's talk about the different spatial scales first. So I already mentioned, so there's the household level or the building level, but then there's a system level. So the system level, this can be the city, a country, or a balancing group or something like this. So this is an aggregate of all the loads within a certain area, for example. And then household or building is, or could be an office building, could be an office. So that's like on the individual level. And here we are typically talking about loads in the, let's say kilowatts. And system level is then megawatts and gigawatts. And what's relevant a little bit, if you go deep into that, is that at the system level, typically loads are more smooth. You can kind of see that in this plot here. So if you average several households, several offices, several buildings, then typically it gets more smooth, because like a lot of these peaks that are happening at the individual level, for example, when you cook, when you vacuum, when you dry your hair, when you use your office printer, then you have these very distinctive spikes into your smart meter data. And the more you average those, these average themselves out. And at the system level, it's much more smooth. This means for forecasting, you have to expect quite high forecast areas if you're trying to forecast individual households, individual offices. So there, like individual households, I mean, I had forecast errors of 100, 150%. So you kind of see this here. If you have smaller loads, for example, individual households, you can expect mean absolute percentage errors of 25, 30% and even more. And the more you aggregate the load and the larger the load, let's say in the megawatts, at the system level, you can go to single-digit percentage errors, for example, for a system load at the city level or a balancing group. This can even go to 2%, 3%, depending on the specific area or if there's a lot of renewables in the system. But then there's also this timely dimension when you talk about forecasts. So there's typically, I mean, this is not very standardized, but typically in papers, you're going to see short-term load forecasting and long-term forecasting. And sometimes you will also hear very short-term forecasting. Short-term forecasting is everything, a day or a few days ahead. Long-term forecasting, typically weeks, months, and years ahead. And sometimes very short-term forecasting can be like during the day. So for example, intraday forecasting, the next minutes, hours. And short-term load forecasting is typically for the next hours to days, which is relevant in, like a typical forecast would be for the next day or a day ahead. So when you're doing forecasting and you're writing a paper in this area, try to kind of think about describing what you're actually doing, because forecasting can be everything on this scale, can be everything on this scale. So make sure you're actually basically making sure what you're actually talking about. And when you want to approach the problem, of course, there's different ways, right? So there's the traditional statistical models like ARMA, ARIMA, ARIMAX, some exponential smoothing methods. We're not going to focus so much on these. And you can actually see them. Also, there's a whole chapter in our book on this. So there's, for example, the benchmark and statistical point cast methods. So this is something you should still consider, right? I mean, the statistical models really depends. If your aim is to really understand the influencing factors, make sure you also check these out. If forecasting accuracy is your main concern, you should definitely look at data-driven methods, but then also look at the more simple methods first, right? So in practical applications, in my opinion, something like random forests, gradient boosting will give you probably more easily the best results. Only if you have a lot of data, if you're doing, let's say you work at some large, like a system operator, and you have a lot of smart meter data, then you may consider also neural network-based models, but also start there with fast feed-forward neural networks, and only then consider the more complex, for example, temporal convolutional neural networks, or something that's more state-of-the-art, like deep AR, NBeats, or transformer-based methods like Informer or Autoformer. And of course, like in other areas now, there's the trend to foundation models, also for time series. So having large models which are capable of handling a lot of tasks. But I would say right now in time series, this is still like really research. And if you're working on the applied side and you want to actually solving a problem, start simpler. Time series, you typically don't need very large models. You can start simple, you can start with statistical models, you can start with simpler machine learning models, and only then go into the more complex models as needed. And maybe at some point also look at these like big foundational models, maybe for prototyping, then also something like few-shot prompting or something may work. But currently, this is still, like I said, research. So this is basically what we talk here about. And also in our book, we have some chapters on both ways of thinking about this. And of course, consider combinations, like if accuracy is really your main concern. Good, but let's jump into load forecasting using machine learning. So here we're going to use the basic data science stack in Python, pandas, numpy, matplotlib, seaborn for some visualizations, stats models, scikit-learn for some of the standard machine learning, TensorFlow for some of the neural network modeling. Of course, I could have used PyTorch as well, but back then I did this in TensorFlow. The cool thing about pandas is that it can handle time series already quite well. So you can, like if you read, for example, so I prepared a small data set for this case study, which you can see here. So it has load, it has a temperature, and it has a date as an index. So this is I think, typical way of preparing your data, getting it into this format. And what you can actually see here, if you look at the date at the index, is that it's a datetime index. So pandas knows it's daytime, and could even tell you something about like the frequency if you prepare it this way. For example, here this data would be in hourly frequency. It knows that it's in UTC, so you can also put it into different time zones. So this is also relevant. Sometimes for load data, it may make more sense to put it into your local time zone. And so this is actually, pandas works quite well for that. So the first thing you typically do, as in any other data science project, is look at the data. And the cool thing about pandas is that you can use it also to go from one resolution to another, or fill in gaps. So for example, here you can use the resample method to make this load data. Let's say, what would it look like if we look at it like this? Oops. This is what I wanted to do. Sorry for that. So currently this is an hourly resolution, but you can, by using the resample method, and make it daily data, and then averaging all the daily values, you can make it now daily data by just one line of code. And then you can, of course, also use interpolation to go to, let's say, 15-minute data. Of course, here you would then have linear interpolation, but this makes, for example, sense if, let's say, your load profile is in 15-minute resolution and your temperature data is in an hourly resolution. You can then interpolate the temperature data to get it down to 15-minute resolution. There's actually a really cool, I mean, it's not part of this summer school, but there's a great tutorial also on the Climate Change AI page, which was presented at iClear 23, which covers how to work with smart meter data. And they cover a lot of the how to prepare, like visualize smart meter data, how to pre-process smart meter data, like combining it with temperature, filtering, normalization, interpolation, outlier detection, and all the cool stuff. Actually, everything almost except load forecasting. So make sure you're going to check this out if you start. And so I'm going to skip this part actually here for now. But basically, this is the great introduction to start there. And if you have your load data then all prepared, and like here we have it in the same resolution, you would then, of course, formulate it as a machine learning problem. So as we know, for machine learning, we want to get it into this form. We need some features, right? So we want to predict what's going to happen in the next hours or minutes. We have maybe a temperature forecast for the next minutes and hours, and how to get this into this form. There you can actually use some libraries to generate some automated features. There's a library that's called TS-Fresh, which can create a bunch of features automatically. It could make sense. In my opinion, that doesn't give you so much control or understanding, or you can maybe generate like, I don't know, hundreds and thousands of features without understanding it quite easily. I would recommend what I'm doing here and creating manually some features. And then doing some EDA to understand how things are relating. And then from the machine learning part, you can use, like we will see here, basically scikit-learn automatically. Or you can actually use some more specific libraries like skTime, TS-Learn, which are libraries which make working with scikit-learn and time series more easily. And then there's one library that I want to highlight, which is called darts, which is also a really cool time series library in Python. So you can actually also work with this and prepare your time series data for forecasting. And they include already a lot of cool models. So they include baseline models, which are typically there. They include the statistical models, which are pretty powerful, like even T-bets or some ARIMA models, the exponential smoothing models, even meta profit. They include the gradient boosting models, the random forests, and then all the complex machine learning models, like deep learning models, like NBEATs that I mentioned, the time series convolutional neural networks. And so this is a good start to have a lot of models unified within one framework. But actually in this tutorial, I'm not using this, but I want to really highlight this, and it may make sense to check this out. Okay, so let's do some EDA. So let's maybe plot temperature and load, and you can kind of see some things. You can, for example, see that obviously temperature and load are related here, right? So the temperature, the load profile is moving with the temperature. So this could be accidental, right? It could be like a correlation, but not necessarily a causation. For example, I mean, basically you have a daily seasonality, and the daily seasonality shows that during the night you don't use any electricity. During the day you use a lot of electricity, and during the day there's also higher temperatures than during the night. But as we will, if you, for example, look at this correlation plot, you can kind of see, okay, there's probably some causation also, because you can kind of see, okay, in higher temperatures there's much more load, and then at lower temperatures there's not so much load. And part of this will be causation, because I assume there's an HC. I mean, this is a typical profile what you see for AC, like an HVAC system, where electric energy is used for heating. If this was a European profile, for example, this would look quite differently, for example, because here we use still a lot of gas for heating and we don't typically have cooling. So for example, here it could be much less correlated. And here, electricity is used for cooling, apparently, and probably not for heating. Or I think this is actually in Texas. That's why it's not getting so cool. Probably there's no electric heating, or it's just used sparely. I mean, something else that you see is this weekly, this daily seasonality. And if you look at the load profile, let's say several weeks, you can kind of see that typically also doing the, what I assume, weekdays, there's a little bit more happening than during the, let's say, weekends, for example. So this shows that there may also be some weekly seasonality. What you can also do there is then look at autocorrelation. So autocorrelation is how much each point is correlated with former points in the time series. And then you basically shift it by 1, shift it by 2, shift it by, and so on, for, let's say, here up to, I think, 200. And then you can kind of see that you have a high correlation with the values before the current value. Then you have a high correlation with 1 day before, 2 days before, and also typically what you see, a higher spike also for a week before, which typically then indicates this weekly seasonality. So this is some typical plots that you can do. But again, also check out the book chapters for some more correlation plots that you can do. But so for the EDA, we say, okay, there's some correlation with the weather that we can use. There's a seasonal component of daily and weekend pattern, and there's some autocorrelation that we should include. So typically load forecasting candidates. So typical load forecasting feature candidates are therefore adding some prior values of the target value to model these autoregressive effects, add some daytime features, something like the day of the week, the month of the year. Maybe you want to include some calendar information, like if it's a holiday, or what we call in Germany bridge days. So for example, if the holiday is a Thursday, typically a lot of people take off the Friday in between. So typically this means for offices, there's less load than on a typical day. And for households, there's typically more load sometimes because you may be at home, or even less load because you're gone for the whole weekend. So you could include these sort of variables into your model. You can, of course, include some moving window statistics. You can model interactions quite explicitly, for example, with temperature. And if you have a forecast of a weather forecast, you can include this into your model. So typically in the literature, weather-related variables, these daily, weekly, and annual seasonalities, then the lagged load, and especially for longer forecasts, it may also be interested to have like information about the socioeconomic indicators, like how many people are living there, if this is changing over time, who is living there, what's the floor space that's available. Maybe if there's interventions, this could be relevant. For example, if there's a tariff and you have a price curve, this could be relevant to include. So this is all some typical that you will see in the literature. And then you want to bring this into this form where you include all these, let's say, for example, categorical values, numerical values, some interaction terms, if you're modeling using simpler models, for example, some derived variables, some autoregressive variables to predict then your target variable, like your load, for example. Make sure that, of course, working with lagged data, you may have some non-values that are relevant. And also we're going to talk for cross-validation that this is also relevant. And then typically, for many models, you can only predict one dimension, but of course some models like neural networks can also predict several at once. So typically what you then have to decide is, depending on your model, what you want to do. So if you have, for example, a neural network that can predict, let's say, for the next hour, in 2 hours, in 3 hours, and up to 24 hours, let's say you have 24 outputs then But if you use like a simpler model, like a linear model, for example, and you only have one output, you have to decide how to model this if you want to do several steps ahead. You can do something like a recursive scheme where you basically take your model, predict the next step, then slide this forward, take the output of the model as an input for the next loop, and slide like this into the future. So this is a recursive multi-step forecasting. Or what you can do is, if you have a model that has multiple outputs, model this directly like this. Or you can fit one model for each point in the future. But then, of course, the models are making these predictions independently from each other. So there's also some hybrid schemes that you can explore, but this is the main idea, that you have to think somehow how to predict multiple steps ahead. And there's also not one scheme that always works better. So that's why this is definitely something that you can work with when doing forecasting with machine learning. And something you should try out. Like, it really depends on how much one model should be informed by the predictions of the other models. When working with the calendar-based features, so something like the month, the day, there's also different options on how to incorporate that into your model. So this is basically this categorical variables. Again, I mean, this is nothing specific to time. This is also something you have to think about with any other categorical variables. But you could say, okay, January, February, and up to December are categorical variables. Then you would do something as you normally do. For example, present them as dummy variables or one-hot encoding, right? So for Monday, you have a 1, and then zeros for all the other ones. For Tuesday, you have a 1, 0 for all the other ones. The problem then there is that, this works. This is typically a good default approach. But, I mean, January and February are somewhat similar, right? And this, because January and February are both in winter. Similar, you could say, Saturday and Sunday are kind of similar because they're both on the weekend. And sometimes, and this closeness is kind of lost here, right? So you could say that for some models, some information is lost. And so you could then do something like encoding it basically January as 1, February as 2, and so on. Then you have this sort of closeness, right? Because, I mean, they're next to each other. But then they're linear increasing, right? And if you're using a simpler model, like a linear model, then this may even hurt the model, because then 1 and 12 are really far from each other. And you also, I mean, you only can model like a linear increasing relationship. And this may actually break your linear model if you do that. But something like a random forest could even handle this maybe. But there's some other ideas. For example, you could, instead of having one variable where you have the numbers, or let's say 12 variables for each, or 11 variables, because, I mean, you can all zeros and all ones. You can model with 11 variables, 12 months. Instead of having that, there's also some in between that you could do by using some sine and cosine functions, right? So you can basically, the idea is also discussed here in a blog post that is linked. You can basically imagine like putting it on in a space where you model this by 2 variables, and you have this basically as a cyclic. By basically putting them next to each other, and then December and January are close to each other in this new space. And this, we will actually see how to do this in the code below. This is again different things you can play around with when actually doing the modeling. Okay, let's jump into the case study. So basically do what I just said. Let's generate some of these variables. So you can see, for example, here I'm doing this for hour and month. I'm creating these variables where I encode the hour of the day and the month of the year. Then I'm including some rolling mean of the temperature. I'm adding the temperature of what happened an hour before. Here the idea is that for temperature, since it's a little bit slower, it could make sense to see what happened before. So for example, if it was really hot in the hours before, it could affect how much you need to consume in the next hour, because these thermal processes are typically kind of slow. Then we can include all the load, what happened in the last hours. Here we just include the load up to the last 24 hours. If you have a more complex model, you can add also the whole last week. We're adding the day of the week, the hour of the week, the month of the year, and the weekends. Dummy encode them to then have this sort of feature candidates in this data frame here. Yeah, so you can kind of look at it, and here you can actually also see what these variables look like, and they look like expected, right? Here, for example, for the hour of the day, we now transformed them into this space with two variables where you basically have arranged them in a circle. We need to prepare the output. Here what I do is we're using the direct forecasting scheme. So I'm just preparing like a 24-dimensional output vector. Then we do some standardization. Here we're using min-max scaling, but of course you can also try, depending on your models, some other processing schemes. Here we use standard scaling. Standard scaling, but you may as well try min-max scaling. I mean, if you're using linear models, you may need some logarithmic transform or box-cox transforms if you want to make your data more normal, depending really on the model that is used. So this is really not different to any other data science task. And here we're doing a basic train test split, but more on cross-validation below. Then we fit some baseline models. Here we are fitting a naive model, which basically takes the value from a week ago as a forecast. So let's say you want to predict for Monday at 3 o'clock. We're using last Monday at 3 o'clock, assuming that this weekly seasonality is really strong and this value is a good forecast. And sometimes it's already, like for some households or some buildings, like office buildings, for example, this could be already a pretty good forecast that is almost hard to beat. But of course, to smooth that out a little bit, we could do something like a smoothing, like a seasonal moving average. What I did here is basically take the last 4 weeks at the same time and average this. So this is now getting already harder to beat. Because now, you don't, like if there's, let's say, some outliers in here, you're smoothing this out a bit. You could even do something like take the last 6 weeks, take out the highest and the lowest value to create a pretty good benchmark. Let's use some forecast metrics. One standard metric is the RMSE, so the root mean square error. Another one is the mean absolute percentage error, which typically gives you a little bit more interpretation, but of course the RMSE is nicer if you to minimize, because it handles outliers better. So let's look at some metrics for the naive forecast and the smoothing and the moving average. You can kind of see they're pretty close. So let's say in percent, where we have what we expected at the beginning. So since we only have 10 forecast errors are still pretty high. So you have 30% for the naive forecast and 30% for the moving average. Okay, but now let's use some machine learning models. Again, like I mentioned already earlier, let's start simple, right? We don't need to start with a neural network. Let's see what a simple model like a KNN model can do. And we fit this, and we can kind of see that if you remember, we're just slightly better than, like if we look at the the mean absolute percentage errors, we are pretty much as good as the naive forecast, right? So this is, not much better. Yeah, so we slightly beat the naive, but we didn't beat the moving average. Another simple model is like a linear model. Here we're using, for example, the ridge regression model from scikit-learn, which has some penalty, like some L2 penalty, which can be a little bit more stable than a standard linear regression on if you have these autocorrelated features like with the autoregression. It's not capable like KNN to produce already multiple steps like the 24 values ahead. So we need to wrap it into a multi-output regressor by scikit-learn, and then we can fit the linear model and calculate it and can kind of see that the RMSE is still not better than the KNN model. Okay. So it does not really improve our modeling here. But before we continue with other models, let's also look at some forecasts. And if you plot your forecast, you can kind of see, for example, the ground truth is here in blue. That, for example, the KNN is maybe a little bit overly optimistic sometimes, but it's getting close. Sometimes then the naive model, like I mentioned, is pretty good, but here, for example, you can kind of see that the naive model overfitted to a specific day a week ago, and that's why it's so wrong here. Similar, the moving average, it's a little bit better because this one day is not as doesn't weigh in so much, but still apparently you have some overfitting to a specific day where there wasn't much load the week before. And this is something that you can then see if you plot your forecasts. Next, it's actually an exercise. So I'm skipping this part here, but now I used a linear model, I used a KNN, and what you could do on your own is now use, I guess, the next level of complexity. Of course, you can use any scikit-learn model that you may be comfortable with, but I recommend trying scikit like XGBoost, like gradient boosting, because typically for this sort of tabular data, it's pretty powerful. And let's see if you can beat those simple models with XGBoost. I have a solution in here. Then, of course, if you use random forests, XGBoost, and so on, typically you have the problem that those statistical models like ARIMA and so on are much more interpretable because you know, okay, what part of the model influenced your output. So what you can do then is something in practice, look at the feature importances. There's stuff like the SHAP values, which you could try. But here we want to use from XGBoost the plot importance method, which could be used to gain some insights into what informed your model. This is, but again, also an exercise. So happy for you to try it out and also check out the solution that I provided here to give you some comparison. Okay, another topic that we talked about was the encodings for categorical variables. So here I modeled the numeric columns using this cosine and sine encoding, and one with one hot encoding. And then we can compare these to kind of see that in this case, the one hot encoding was better than this sine cosine encoding. Again, something that I mentioned, there's no one best way. Sometimes the one works better, sometimes the other. It's something you can try out. And here, one hot encoding worked better. Good. So this was like some simple benchmarks, like the using 1 week ago and the average of the last weeks, and using some simple machine learning models like KNN and a linear model that could be a good starting point, and then using something like XGBoost, which you tried yourself, hopefully, to see if we can beat these models with some standard machine learning model. Good. But now let's look into neural networks. And again, as I mentioned, we're going to use TensorFlow here. Of course, if you're at PyTorch, then do it in PyTorch. It would be kind of similar. But here I like using this Keras API because, yeah, I think having it written like this for me, it's just nicely. But I don't know, like I don't want to get into this discussion here. So what we do here is start with a simple sequential model. So what we need is some input layer that has the shape of the input. Then we add two hidden layers here, one with 15 units, one with 5 units. So you don't need really deep neural networks for time series, especially at the start. Do some ReLU activation here. And then since we have a regression model, we want to have the last layer as a linear layer and use as a loss function the mean square error. So this is, I guess, what makes sense for regression problems. And then, this is what the model looks like. I mean, it has 1,200 parameters, so far away from these millions and billions of parameters that large language models have. And we can even go simpler with that, right? And then we can fit the model, train the model, and see the prediction and the ground truth, and we can kind of see that a neural network can also model this, and we can kind of see that the mean absolute percentage error is still not better, like the 18.49 is still not better than what we had up here with the, I mean, we are now better than we're now better than the naive models. But we're not as good as the KNN and not as good as the rich regression. Okay, sorry, I kind of messed that up earlier. So the KNN beat the simple models. Rich regression didn't meet the KNN. And now we can see that the neural network is not beating the KNN model in your first attempt. So what could be happening? Like I mentioned already, like we're having one time series here. It's hourly resolution. So we're probably overfitting, right? So it's not a lot of data. So that's why we could try to make this model a little bit simpler and try to beat this. So this is actually something, I mean, we can actually also look at the training curves and can kind of see, there's a large gap between the training and the validation loss, and the validation loss sometimes even increases a little bit. So it may make sense to try to tune this a little bit. So you can try a smaller architecture. You can try different regularization methods to avoid overfitting. And you can train the model on more data, right? So you could use now the data of other households to get more data. And of course, you can also go back to the features, for example, include a longer time window. And actually, I mean, more data it's not part of this tutorial, but exercises 3 and 4, again, up to you, are really trying for you to get this model better than the KNN, basically. So you could try to, for example, take out one of the hidden layers. You can add some dropout, for example. And of course, you can also try different things like early stopping, batch normalization, whatever you can basically think could improve this model. For now, model size and dropout is the one that I tried also in the solution, but I'm happy for you to try other things. So for example, here, the initial model, I could, in the solution, I could fit a model that improves upon the initial solution, but don't look at this now. First try on your own and try if you can improve the model even more. Then exercise 4, you can actually see that, I mean, since up here you can see that it's not improving much after the first iterations, you could also try something like early stopping. And this is something which, again, if you know how to do, you could try yourself here and then check out the solution. I mean, yeah, check out early stopping for Keras, and I think it should be feasible for you to add the code here and here. And then you can just check out the solution and then to see if you can even more improve it. But I mean, the main takeaway, I guess, here is since you only have one time series, it's 1 hourly data. I mean, you can improve upon those simpler machine learning models, but you're not gonna improve by a lot. So for that, you would need more data. And this is typically what then is referred to as global modeling. So for example, if you have one building that you want to make the forecast for, but you have access to the data of a lot of buildings, then you could fit a neural network on all of that data and then make the forecast for that specific building. Then there's even hybrid schemes where you combine, for example, you train a model only on a subgroup of the data that is kind of similar, like you cluster the data first. But yeah, again, check out maybe in the book, there's also a short chapter on that, but there's of course also some papers linked in the book that are doing more state-of-the-art things. Good. One thing that we already talked about when we have a first forecast is to kind of look at basically the forecast, calculate the metrics that we did. But of course, like there's other model diagnostics. Just also briefly here, more again in the book, but something that you could check is that residuals should be uncorrelated, because if there's correlation between residuals, so the errors, then there's information left which could be used in the model. Residuals should have zero mean, because otherwise, yeah, you also have a bias that you could basically subtract the mean of that, and you should have a better model. And there's some properties that could be useful. So you could check that the residuals have constant variance. There's statistical tests for that, and that the residuals are normally distributed. So that's something you could also try. For example, here from the Forecasting Principles and Practice book by one of the forecasting gurus, Robert Heinemann. Yeah, you have basically example plots, but of course it's easy to do this in pandas. You can get all the errors by taking your prediction minus your expected values, and then look at the distribution, and you can kind of see, yeah, this is not very normally distributed. You have some skew here, and you have a small bias since the mean is not completely zero. Also, if you check the autocorrelation plot, you can kind of see that there's some significant autocorrelations that are not included in the model, right? So especially from the last day, there's some statistical some correlation that could be used. 1 week ago, there's some autocorrelation that could be included, for example, in the model. But this is again something that you could try. So main takeaway message, like I said, start simple, but with not too simple, right? Include some strong benchmarks, especially if you're writing a paper. Don't just use like a naive model. Use also like seasonal models, maybe some statistical models like ARIMA or seasonal exponential smoothing models, or some simple machine learning models. And then only go to your favorite complex LSTM, CNN transformer that you that you build. Because if you just use like an LSTM compared to a CNN, it's kind of hard to know how to put this into perspective, into research. This is maybe a critique also that we wrote about in this survey paper, is that there's no established benchmarks in this area. So that's why don't just compare your favorite CNN with an LSTM, but compare it also to some seasonal models, statistical benchmarks to put this into perspective. Yeah, don't just look at the RMSE, but also look at the forecast, create some diagnostic plots to see where your model still fails. And then try to iteratively improve your model. Okay, let's go to the last chapter, and here just briefly 2 things. One thing that I've actually also seen too much in papers is when you only want to forecast 1 step ahead. Especially, let's say you have what I've seen, for example, is forecasting very high resolution 1 minute ahead. And you're always making this 1 minute ahead prediction. And to show the point that I want to make, let's move away from load forecasting. And for that, I downloaded a data set that's actually stock data. So I have the Apple stock here. It's the closing data, and for several years. And it looks like this. And let's consider another stock that I call, let's say for now, stock 2, which looks like this. And let's fit some simple model similar to what we did. So we creating some legs up to, let's say, the 7 past values. And we fit again like a simple linear model and make a prediction. And now you can actually see here a prediction for the Apple stock. And we have a mean absolute percentage error of 1%. Let's do the same for the other stock. And we have a mean absolute percentage error of even less than 1%. That's awesome, right? Now we can forecast stocks, less than 1%. That's pretty cool, right? That should give us some big money, right? Well, of course not, right? You can kind of see this. It looks close, but you can kind of see that it's basically the same, almost just shifted by one value, right? And still, since, they are so close and you have no large jumps between 2 time steps, that's why the errors are still pretty low, like in absolute terms, if you look at it. And stock 2, if you look closely where I created this data, I didn't tell you at the beginning, but if you don't believe me, it's completely random generated data. So, of course, you can't predict random data. I don't have to tell you that. And this is basically the point that I wanted to make here is, just looking at the mean absolute percentage area here doesn't make sense, right? It doesn't inform you so much. But I've actually seen that in papers. And something you could do, for example, first to get some indication is using, again, a naive model. And here we, let's say, have the naive model that is the persistence model. So we have always next step is what we ever had in the step before. And if we do this, then, it's the same, just shifted by 1 step. And here you can see that this naive model also has a 1% error. And now you can see, and for the other one, it has 0.85%. And now you can see that, okay, here, this one beats it, which is, not significant. And this one doesn't beat it. So you can kind of see that this now indicates, since you're not really beating significantly the naive model, that your forecast model is currently not really adding any value. Something that you could do now is look at the autocorrelation, and you can kind of see that there's that there's of course this autocorrelation, and for the random walk this is expected, right? Because you're always starting some point and going from there up or down, and this means of course that the value before that is still correlated, but it doesn't give you any value. So okay, now let's get into what you should do instead. The time series, it's moving up and down through this random walk, and you could argue that stocks are also in a way random walks. And what you need to do is now to make this time series stationary. By that you can do by removing the value of the previous observation from the current observation by differencing. And by that you're taking away this whole movement together out of the equation. And that's why you should check if your data is stationary. And load data typically could be stationary, but it doesn't have to be, right? So it could be that, for example, over the month and years, the whole load in a building is increasing because more digital devices are bought. And if you difference the data, then it looks like this, for example. And for the random walk, it looks like this, because I only moved up one step or one step. And now you can see that if you create an autocorrelation plot, there's no significant autocorrelation for this data, which means, that we can attribute the statistical mistakes, to randomness, and both of them are now, it shows that they are basically a random walk. This is just something to keep in mind when doing one step ahead predictions. Basically, the main message being, make sure that your time series is stationary, and if it's not stationary, you may consider differencing your time series first and then doing the forecasting. Good. The second pitfall that I wanted to talk about at the very beginning is now cross-validation. I've shown you already, there's different models you can try, there's different features you can try, and so it's important to not overfit to a specific data set that you, like if you especially want to try different of these different versions, to come up with a good cross-validation. And there's generally different things that you can try. And of course, this is also true for general data science, but for time series, you have one problem. And one problem is, let's say, if you think of your standard cross-validation, where let's say you want to make predictions for this block here, there's two problems. One problem is that when you're building features where you're including autocorrelation, for example, you're typically at the borders have the problem that you're averaging in something from the past, right? And this typically means basically a leak from the training data set into your test data set that you have to make sure. Also, you're kind of cheating in a way because you're training on data from the future to make predictions in the past, which there's also some theory that this is also unfair. But then, so something you could do then is basically do this, where you're basically not using the future and only train on the past. But then this means that in some iterations you don't have a lot of data, and in other iterations you have more data, which also makes then some of the other assumptions that you want to have is that they follow a similar distribution. It's kind of hard. Let's say you have only a year of data, then here you include only the winter. Here you have winter and spring. Here you have winter, spring, and summer. And you have winter, spring, and fall. So then the distributions may be quite different. So this scheme may only work if you have a lot of data. This scheme is therefore maybe still the better one, because then here you can throw away some of the data around the edges to avoid this leak from the past. But you use all the data and you use all the seasons. But then also, again, here you may have the problem that it's summer and so on, and this is winter. So sometimes it makes sense to come up with really your own scheme, like something like this, where you separate the test sets over the years, for example. Let's say if this is 1 or 2 years, that you have different weeks over the year. And then again, make sure that you throw away some of the data around the edges to avoid the leak into the test set. I actually have a reading on this below, so this is just really for now, just to show you that there may be different results. Like here, I'm setting this up again, like above, using the KNN, using a grid search on parameters, and here, depending on what cross-validation you use, you may get different results. And if you look at the errors on each of the test sets of the splits, you can kind of see, for example, what I already mentioned, that, for example, with the time series scheme, you may have very different errors for each of these blocks, because like at the beginning, you may have had only a few data, and later you have more data, and more data. And similar for the blocked, you may also have some variation because, some of the blocks don't include all the seasons. And then if you shuffle it completely, it's nice. You have this distribution, but then, like if you want, like here, I think I included all the autocorrelation data, so I may have created a leak. And if I wanted to throw everything away right before, then you're throwing a lot of data away. So this is the sort of trade-off where, again, there's no perfect answer, because it really depends on Do you have 1 year of data, 2, 3, or 4 years of data? And then you kind of have to think about to make sure how to have some setup where you make sure that you don't have leaks through the autocorrelated features. You may want to throw away the feature when training, but typically this is something where in my experience it still works okay if you do that and you don't have to throw away so much data. And typically you want to make sure that your test set includes all the seasons, like that your test set is not just summer and the training is in all the other periods. So it may make sense to sample your test set over over the available data. So here I can just show you that there's the reading 3 here, forecast evaluation for data scientists, common pitfalls and best practices, which discusses this in length. There's actually this Christoph Bergmeier, he has 2 or 3 papers on that topic. Good. So this is the main messages from the pitfalls section. For one step ahead forecasting, be careful. There may be an illusion of a good forecast, even if it's not. This is the case if the time series is not non-stationary. So you may have to work on the difference series if it is a non-stationary time series. And then there's the cross-validation scheme that you have to think about. It really depends on how much data you have. Make sure that you have all the seasons of the year included and make sure that you're not creating leaks through the autocorrelated features. For example, if you have a long window in the past, make sure to have large blocks so you can cut away these parts. But I recommend reading this paper. Good. Like I said, I mean, I didn't tell you what's the best model for your specific problem, but I hope I gave you some insights into things that you can try, things that you should think about, and gave you some starting point for also some reading and playing around yourself with the models. If you want to do research in this area, one thing that I already mentioned, there's no proper benchmarking. So you could be the one writing the benchmarking paper. I mean, I have me and some former co-authors, we always wanted to do that. So maybe reach out to us also if you're interested in that. Yeah, try state-of-the-art deep models, right? I mean, this is an interesting pathway, especially if you're thinking foundational models. Try if they could beat statistical models also with something like few-shot prompting or something. Could be interesting, but right now I would say simpler models are still winning if you don't have a lot of data. Probabilistic models, something that I've also done. I mean, I already showed you that there's high errors, like 30%, 40%, 50%. You could argue, is that a useful forecast? Maybe like a point forecast, like just having one value predicted, I mean, may not be useful. So having a distribution, having quantiles could then be used maybe by optimizations like robust optimization, stochastic optimization. So this could be an interesting way, especially if you want to do more complex models. Like I used some generative models like normalizing flows there because sometimes, especially on the household level, you may have several modes. So you have then some interesting distributions that you could try to model with machine learning models. Then the power system is intrinsically hierarchical, right? So you have households are in a building, buildings are in a low voltage grids are in a high voltage grid. And so you could think about hierarchical models, graphical models that model this. Power grids are typically also ring structures or graph structures. So this could be interesting to kind of see if graph models can be utilized. Multivariate models, typically you have a lot of different, like here we had temperature and load, but of course there's maybe also thermal loads, electric vehicle loads, and modeling these all together could be an interesting research direction. Doing online forecasting could be, for example, if you have a home energy management system running embedded that's not connected to a cloud, this could be interesting. Some more readings to continue reading, like I mentioned already, this review paper and the book. I mentioned this book. There's also like a book more focused on R by Robert Hindman. on forecast principles in practice. I mean, there is some overlap, but yeah, this is general time series and we focus on load forecasting. And yeah, there's also a good blog post if this is more your thing. Tools in Python, I already mentioned the other tutorial that's available at Climate Change AI, working with smart metadata. This is really useful if you really want to get started. Like, they have a lot of like code snippets that you can start. I already mentioned Tiers Learn, Stats Models, Tiers Fresh, Facebook Profit, and Darts. These are all cool libraries, so you don't have to do this all manually. Some of the parts that we did, really check out Darts. I mean, it's really cool. Then visualization. I mean, use all the Python libraries. They all handle time series data. In R, check out Robert Hindman. He's the time series, I mean, I don't want to see God, but I guess one of the significant people in this area. So he has written some of the most influential R packages, like the forecast package, which is now in the tidyverse, Fable and Feasts. Really check out his things. If you want to get started with data, I recommend two things to get started. One is, again, something that I've created. So here's a list of load data sets, which also contain building data sets. So by now I have 73 data sets in here. Check them out. You can filter them also by a region, for example, like Germany. Then you get German data sets. If there's data sets missing, let us know. We can add them also. That would be really cool. And then there's the Monash time series forecasting repository, which tries to be like a benchmark for time series data. And they also include some building data. Okay, with that, I want to conclude this tutorial. I hope you enjoyed the tutorial. You learned something to get started in the area of load forecasting. Have a great attempt at trying the solutions to these tasks. Maybe hit me with a message to let me know how it went for you. And have a great summer school. Thank you.